scroll down a little bit. They're looking at. I would say it's a mixture. Colloid. So is fog. All the fog we've experienced lately, driving here in the morning, is colloid.
I thought it was just gas.
Nope. It's a mixture of different types of air and water vapor. So, people who's driving? Who's a driver? Oh, poor babies. Okay. So, are you supposed to put your high beams on in the fog?
No.
Why can't you see? Why can't you see? Because all the particles in the air actually refract the light and move the light into multiple areas, so it makes it more invisible. So just put your low beams on, or just drive with no lights. No, I'm just joking. Don't do that. So, put your fog lights if you have fog lights on. Okay, so for solid, liquid, and gases, we know a lot about them in terms of their phases, their properties, but we need to talk about them on the molecular scale. Basically, what do the molecules look like? Zoomed in nanoscale, okay? So we know these are tightly packed. We know these, the solids are tightly packed. These have no set structure, so no shape, but they have a set volume, right? This one, the solid, has a set volume and shape. So that one's, we could actually draw like a cubic crystal or something like that. The liquids have abilities to flow, meaning that they are not set in a specific structure. Solids cannot flow, but they still have energy. We know that, you guys know all the molecules in your body. If they were not attracted to each other, the molecules in your body were not attracted to each other, I could walk right through you. How awesome would that be? Like, excuse me, get on the way. No, I'll just walk right through you. Right? That would be cool.
Is that how ghosts work?
That is how ghosts work, yeah. That's true.
Wow.
But the molecules in your body are vibrating at a specific frequency. They also have attractive features to one another, so that's what holds you together. But if they didn't have any attractive features, the vibrations would essentially just allow for our molecules to pass by one another, which would be really cool. So they do have vibrations, which just means that they're slightly energized. So you see this whenever you microwave food. So the food that you have, like you put in the microwave, it's probably frozen, right? You're warm enough something frozen. How does it get hot? Okay, so cold particles have really slow vibrations, just like kind of like this low kinetic energy. Cold particles. As they get warmer, they start vibrating more. And as they get warmer, they vibrate more. Whenever they vibrate more, they bring upon themselves more like higher heat, which is aka just temperature. So the only way the microwave works is the microwave, what's a microwave, by the way?
The waves microwaves.
It's just straight up energy. Okay? Like on our electromagnetic spectrum, it's just energy. The energy is kind of shot through the water molecules in your food, because all food has water molecules in it. It vibrates them, it makes it feel warm. Okay? So what if you got in the microwave? What's your body made of?
Water.
Water. Your body would be shaking, violently shaking, and then you would probably explode. Okay? There's an actual microwave at UNC Charlotte.
My cat ordered, like, I'm gonna put it in the microwave.
Don't stop. Okay, so at UNC Charlotte, they have a microwave for their chemistry lab, but it's a microwave projector. It's not a microwave like an enclosed food microwave. So the beam of microwaves, like the energy just comes right in front of your face, and you just put a sample in there and you microwave it, because you have to like sometimes microwave different metals, and you can't put metal in the microwave, right? It'll spark. Okay, so you can't put it in the normal microwave, so they have a beam. But if you put your hand in the beam, it will like blow off a finger. So we have to get you have to pay like $200 to get certified on their microwave beam, because it's so dangerous. So that's just a fun fact. Okay, so with gases, let me go down here. Gases, we know that they have no shape, no volume. No shape, no volume. They take the volume of their container. They don't have a set volume is what I mean. And they have rapid motion, right? So they're constantly randomly moving everywhere. They're the most energetic, oh my gosh, of all of our phases of matter. So basically what you'll see on this left-hand side is I'm showing you kinetic energy is increasing as you go down the different phases of matter. Lowest kinetic energy, medium kinetic energy, highest kinetic energy. So that's more about the molecules themselves. Now let's talk about how does the environment play impact upon the shape, the volume, etc. of the solid, liquid, and gas. So if I increase the pressure or increase the temperature on a solid. So you got a solid in your hand right now, right? Increase the pressure on it. What's happening? Nothing. Okay, increase pressure, no change. It's because the molecules are already so dang close. They're almost touching because they're so close together. There's no change. If you increase the temperature on it, it depends on how hot you make it, right? But generally increasing the temperature, they'll get a little bit more energetic, just bounce around a little bit more. But there's generally no change. But you can heat it up to the melting point. You can. Just depends on how much temperature change you're causing here. Yeah.
What about like when you bend something and it's hot?
That is kinetic energy. You're adding kinetic energy to it. Kinetic energy is heat. So you're making it have more motion, like a rubber band. Rubber band's elasticity, they'll get hot when you stretch them like 100 times. So the only thing I do want to mention here on temperature change, you can have something called thermal expansion. Thermal expansion. So, trying to keep this together here. So that basically means, that's together, you have like an engine block, for example. The engine block in your car gets hot, the bolts and stuff that are holding it together, it would be almost impossible to pull it apart while it's still hot. You'd have to let it cool down, the engine cool down, so that the metals contract back to their normal state and normal shape, so that you can actually, unscrew a bolt or a screw or something like that. So metals have a lot of thermal expansion abilities. Liquids, we say increasing pressure, increasing temperature. Pressure generally will not do much to a liquid, okay? You'd have to severely increase the pressure to cause a change. So this one again, generally no change. Increasing the temperature on the liquid, again, generally no change, but you do have those exceptions. If you heat it up hot enough, what's it going to do? Evaporate to gas or boil. And if you heat it up, there can be something called thermal expansion again. Okay? Just the molecules expand. They just move apart from each other just a hair, just a little bit, nothing crazy. So the last one, what do you think is going to happen here? What happens when you increase the pressure on a gas? Say what? It compresses, right? So everybody got a box of air? You got it with you today? You brought it, right? You got your air? Okay, compress it. Increase the pressure. So the volume definitely went down. There's an inverse relationship there. There was a big change in volume. Oops. If you increase the temperature on your box of air, your air right now is moving at a constant kind of general speed. Increase the temperature, what happens to the molecules in here? They get crazy, okay? And when they get crazy, they push away from each other. So the volume can actually get larger because they're increasing the kinetic energy, which will increase the volume because they start to move apart from one another. It depends on if they're in a closed container. And our container is obviously not closed. See, it's open to the air. All right, and I'm going to skip this part for now. I'll say that again when we get to the point. All right, so that's all you, yeah?
Why does high temperature feel?
Because the kinetic, why does high temperature feel, it's
like
more...
They're moving faster, so more friction or what?
Okay, so there's no such thing as cold. Basically, the more kinetic energy a substance has, and if it's in drastic contrast to whatever the kinetic energy the other substance has, you feel the difference. It's not that you're feeling the heat, you're feeling the difference between the kinetic energies. So it's a different level of energy bombarding another substance. Boom. We'll talk about that when we get to thermo. Okay, so this is a picture to explain exactly what I just said. Okay, so as I phase change from solid, liquid to gas, is that an endothermic process or an exothermic process? Look at the molecules, people. It is, because we're at low kinetic energy up to high kinetic energy. And so you put energy into it as you go across, so that's an endo process. So if I went backwards, went from crazy gases to liquids to solids, it would be exothermic process. Does that make sense? Yeah? Okay. So that's what we're doing down here. So I'll get to that in just a second. This is important solely for the purpose that we know we have the power and the knowledge to change any phase of matter to any other phase of matter by changing two variables. Or we can do it with different variables. Generally, you can change the pressure of something drastically and or the temperature of something drastically, and you can actually change it to another phase of matter. We're focusing on temperature today. So write down what you want to from that statement. I'm going to start saying yeah, see that's delta H, you get delta S, we need delta E or something, but there are some things delta E changing energy. Yeah.
Could you get liquid oxygen into your veins and survive instead of
Where are you going?
The concentration, okay, so it would diffuse into your cells because the concentration in your veins would be higher. It would become attached to hemoglobin. It would be delivered. It only is based off if hemoglobin will take on liquid versus gaseous oxygen. Like, I don't know if the energetics is...
You take, like, oxygen pills.
They have oxygen bars before exams in, like, college. You go and, like, to inhale a bunch of oxygen because it's supposed to, you know, be more energy, and your brain uses 50% of your glucose a day. Yeah, you know this? So if you don't eat, you feel really tired, and your brain doesn't work very well. So eat before my class, please. Yeah, so your brain needs more oxygen. Eat before my class, please. And so they have those so you can take in more oxygen because you need a lot before, you know, if you're overusing your brain. But if you have too much oxygen, your brain shuts down. So I don't know about the liquid oxygen because it might be a bad thing. You try it. You let us know.
Well, wouldn't it be like really cold? Or like GNC has or O2 pills.
O2. I don't know if that works. GNC. That's not FDA approved. Not FDA approved.
Workout pills.
Interesting. Okay.
Approved, but let's
Back to here. Okay. Okay. We're going through this part fast. Ready? Shh. Okay. Low, medium, or high kinetic energy. This solid here. Low kinetic energy. This guy. This is a liquid. Medium kinetic energy. Okay, so is that endo or exo process? You're going from low to medium, so that's an endothermic process. Okay, what process is this? What phase change is this? Thank you. Solid to liquid is melting. Melting. And this has a delta H associated with it. That's a positive or negative number. Positive number. Endothermic is a positive number. You're inserting energy into it. Drop it there and then work with me here, okay? All right, so notice the next one. What can you tell me immediately about it? Everything's the opposite, right? So you have medium kinetic energy goes to low kinetic energy because we're going from liquid to solid. So what's this next part? Exo, freezing, delta H negative. Okay, this delta H has a name. You need to know the name of this delta H. It is called enthalpy of fusion. This delta H's name is enthalpy of fusion. This has a value as well. It's specific for any given different substance. So water's delta H of fusion, I would call it delta H fuzz, is different than like carbon dioxide's delta H fuzz, which is different than oxygen's delta H fuzz. It's just different. But the units are always the same. And what it's talking about is always the same. It's talking about the phase change of melting or freezing. So the number, aka the magnitude, of this delta H is the same for both of these processes. What's the only thing that's different about this delta H? It's negative or positive, right. So for water, for example, the delta H of fusion for water is 6.01 kilojoules per 1 mole of water. So the fusion, which is melting, is an endothermic process, so it's a positive number. But the freezing is the opposite of that with a negative sign in the front. Yeah.
What exactly is the H?
Delta H means enthalpy.
What is it?
The it's supposed to, it's like they give symbols. It's related to heat. It's not all about heat, but it's related to heat.
Yeah, those things change.
Yeah, so they call this this enthalpy, which is related to heat, but delta S, which is entropy. S came from something called spontaneity. They have some meanings behind their variables, but sometimes no. There's not a whole lot. But it's very specific to 1 mole of a substance. That's the only part I want to tell you about. All right, cool. Next page.
I have a question. For X, like the very first one, endothermic means you're gaining heat, right?
Gaining energy.
Gaining energy. Oh, okay.
Energy and kinetic energy, heat, they're all directly related. Okay, vaporization. Fast with me here. Liquid, medium, high, or low? Medium kinetic energy. Gas, high kinetic energy. Change. Endothermic, because you're inserting more energy. Delta H is
Negative. No.
positive, inserting, entering it. And this phase change is vaporization. Okay, next one. High kinetic energy to low kinetic energy. I'm sorry, medium, you're right. I'm going with my trend I've started here. Okay. Exothermic process. Negative, and this process is condensation. All right, so things I think are making sense in terms of our energy here, right? This one has a name. Let's go with the flow from what we just learned on the last slide. This one's called delta H VAP. Vaporization is what that means. So tell me the definition of this. The energy to vaporize or condense
1 mole.
Good. 1 mole of a substance. So, what are the units again for delta H's? Always. KJ is kilojoules per
Mole.
1 mole. Right. Always those are the units, okay? So, the only difference, this one for water is 40 point, what was it, right? 40.6 kilojoules per mole. That's that for water. So the positive version is representing the vaporization phase. The negative version of that would represent the condensation phase. So they're off the same magnitude, opposite design. And this is a fun fact I need you to know. Because if you want to use the words vaporization, evaporation, and boiling, then you need to use it correctly. Okay? So you're boiling spaghetti. No, you boil water. You don't boil spaghetti. That would be gross. Water. You're boiling water. Where does it start boiling? Where in the pot? At the bottom. Okay, because you're heating it on the oven, stove, and then you boil it from the bottom to the top, right? So it's boiling throughout the substance. So boiling is always occurring throughout, not at the surface. The boiling point is reached when the surface starts to bubble off. But boiling occurs throughout. Evaporation occurs at the surface of any liquid. Evaporation cannot happen internally, because where's it going to go? Where's the gas going to go? It's going to try to make a bubble, but those don't have enough energy. So this is important because who has ever experienced the burnt tongue of eating soup? Most of us, okay? It's an awful experience, right? So what we try to do, vapor. Vapor is a gas which has high kinetic energy, right? You have your little soup spoon, and there's some soup in here, okay? What do you do to it before you bring it to your mouth to eat it? Why do you blow on it? But there's no such thing as cool. Make it less warm. So what are you blowing away? What energy? Okay, so you're blowing air of just like that's going in one direction on these little vapors. The soup has vapors coming off of it, right? Vapors are the highest kinetic energy of all the states of matter. So these little vapors up here have high kinetic energy. If you blow them away, they're out of the picture, leaving behind overall lower kinetic energy. Lower kinetic energy means lower temperature. So what you're doing is you're blowing away the fast-moving particles from your soup. Does that make sense? You're blowing them away because you want them to overall be a cooler temperature. So that's why we have to know what vaporization is. It occurs at the surface. And so we can respect the soup. We know how to make it work. All right, so I'm skipping vapor pressure for now. Let's do the last two. Okay, so this one's the phase changes that are skipping liquid phase. We're going sublimation, deposition. Sublimation is, tell me again, low to high kinetic energy. Endo or exo? You're increasing the energy. Endo, delta H is positive. This is sublimation. This is going directly from a solid to a gas, no liquid phase whatsoever. So, my dry ice is already like frozen the outside because there's water vapor all around us, right? So it's frozen the water vapor and made frost. So there's deposition.
Snow day.
There's deposition.
No.
And sublimation. Let me get some water. And here's sublimation. So there's dry ice in here, which is just carbon dioxide. Don't breathe in all the carbon dioxide. It won't set on fire. This is carbon dioxide. I just don't want to pour water on something because I did that last period. So there's water in here. So there's sublimation for you. Did you see? I only put water in there to make this stuff boil. Okay? So there's carbon dioxide coming off of the solid carbon dioxide in there. So it's actually the dry ice in there starting to freeze the water that I just put in there because water's boiling or freezing point 0. So this dry ice is probably at like negative 80 degrees Celsius right now. I'd have to look at the phase diagram. So it's freezing the water, but you see you can probably hear it bubbling. You hear it bubbling? It's because it's boiling.
No way.
Yeah. It's boiling. Boiling is simply a phase change. Boiling of water happens to be at a hot temperature. Boiling of carbon dioxide is at a fairly low temperature. What's the boiling point of carbon dioxide? Here's carbon dioxide's phase diagram. It's getting violent up in there. And the phase change, let's see here. I don't even have 1 atmosphere here. No, sorry, here's 1 atmosphere. 1 atmosphere, there is no, it goes straight from solid to gas, so there's no technical temperature, whatever this is. 198 Kelvin is what in Celsius? Like negative 80. I was almost right. 73 down to
I am smart.
2, 3, 76. Negative 76 Celsius.
Like 40%.
So that's what that's subliming at. Okay. Anyway, so sublimation is going from gas directly to solid directly to gas, and deposition is opposite of that. So this has a delta H of, guess what? Delta H. I'm just going to label it, sorry, delta H sublimation, which is the energy required to cause sublimation to occur of 1 mole of that substance. So energy needed to sublime or deposition deposit 1 mole of substance. So sublimation is endothermic and deposition is exothermic. States of matter done. Now, we have to analyze graphs. This is on your paper. I'm not saying it's a pretty graph. It's kind of splotchy because my copy was dark. I'm going to talk about this in just a moment. Okay. All right, so phase diagram. Make sure you know that this is called a phase diagram. And a phase diagram is specific to one substance. So there's a different phase diagram, a different graph like this for every substance in the world. Water, carbon dioxide, oxygen, those are my common ones I'll just talk about for now. So they have 2 different conditions that are always changing. You'll see that the y-axis is pressure, and the x-axis is temperature. But the substance itself is staying is what it is. The phases of matter change though. So as you go from solid to liquid, what's that phase of what's that transition called? Melting, and then liquid to gas. Vaporization or boiling, whatever you call it. So it's always in this general scheme. It's kind of like a little Y shape in the middle, and it goes solid, liquid, gas. Always. Okay, the locations where the states of matter never change. You've seen these before? Middle school? No. Lies. They lied to me. Okay. So this is called a phase diagram. Solid, liquid, gas in this specific order. If I say normal atmospheric pressure or normal temperature or normal pressure, when I say normal, I'm talking about normal that we live at. We live at 1 atmosphere. That's our pressure. So if I ever say the word normal, know that I mean 1 atmosphere. So what is the normal boiling point? Let's do melting point. What's the normal melting point of this substance? What you would do is you go to the pressure of 1 atmosphere and you draw a line over to the point where melting occurs. The melting occurs between the solid and liquid phase. So this point is the melting point. But what temperature is associated with that? You drop it down and you see it's 0. So what substance is this that melts, or aka freezes, at 0? Water, okay? And then continuing over, if I want you to find out the normal boiling point, I go over to the transition between liquid and gas. That's my normal boiling point. Drop it down, yet again, 100 degrees Celsius, so this is water. So this is a tool to help you find different points of transitions at different pressures. So if I was under the ocean, what would my pressure be? Higher? So like up here? So like maybe 3 atmospheres? It's probably like 30 atmospheres. I'm going to go with 3 for now. So where would water boil under the ocean? You take your 3 atmospheres, draw it over to the boiling transition, which is between liquid and gas. It would boil at, I don't know, 120, whatever that number is there. So you can see it's going up here. You can just read a graph. That's what this is. If I was on top of Mount Everest, what would be the pressure?
Very low.
Very low, like maybe like 0.1 atmospheres. Basically, if you're on top of a mountain, you've got much less atmosphere above you, so less atmospheric pressure pushing on you. If you're beneath the ocean, you've got the full atmosphere plus the ocean pushing on top of you, so you've got a lot more pressure. So most people forget about the differences there. But the 0.5 would be like down here, and you would see that, does water boil below 1 atmosphere? Or below, where am I at? 0.5. Does water boil at 0.5 atmospheres?
No.
It goes straight to sublimation. It does not boil. Because there's no liquid phase here. Yeah.
Like, how come it's harder to boil water in the mountains?
Okay. I need a... All right, Colin, be my atmosphere. Come to me. I need you. Be my atmosphere. Okay, so he is the atmosphere. He's raining down on me. Ready? Let's stand this way. Okay, be the atmosphere.
Well, I gotta be so fresh.
Okay, you're pressing down. Okay, he's like really strong atmosphere, right? All right, so water, I'm water. Be strong, man. Okay, so I'm water. At normal atmosphere, at like 1 atmosphere, water eventually will get heated up hot enough, kinetic energy is increased enough, that the kinetic energy can surpass the atmospheric pressure, right? So this is when boiling happens whenever we go like this, okay? So if the atmosphere is pushing down on me like under the ocean, the water has to put forth, it requires a lot more heat to, a lot more heat, so a higher temperature. You have to put forth a lot more temperature to make it boil, right? But when you're up here at a, what'd you say, high on a mountain, it's not necessarily that it's harder to boil, it's that you still have to heat it up, because it's actually easier to boil. So whenever you're up here, water will put forth like 99, so maybe you heat it to like 95 degrees, and it will surpass, the kinetic energy will surpass the light pressure up here. So it's actually, the boiling point of water is, you're good now, atmosphere, thank you. The boiling point of water is actually lower at lower pressures, lower atmospheric pressures. And the thing that happens is if you put other solvents in there, solutes in there like salt, the boiling point increases because the salt's playing with the water and not allowing it to evaporate. We're going to get into that like in 2 units. Hold it. Okay. So, I mentioned here. Do we know that this is called the triple point? Triple point is when all 3 states of matter touch each other. Okay, so solid, liquid, gas touch each other at the triple point, so that's right there. And then this right here is called the critical point. This is on your reading guide. What was the critical point? Do you remember the definition?
Like the equal?
So it's talking about the two phases of matter that are up here. So it's stopping there because the distinction between liquid and gas they're only distinguishable up to that pressure and that temperature. Once you surpass that pressure, the pressure is pushing so hard on the gas it's trying to push it back to liquid. But the temperature is increasing so much that the liquid's trying to go to gas. So it's this fight between solid and liquid, and so it's an indistinguishable state of matter. You can't tell if it's liquid, or you can't tell if it's gas. It's indistinguishable. It's like this liquid. There we go. That's what it is. Yeah.
I'm probably relating this to something completely different, but is it like when you have, I don't know what it is exactly, it's like flour and water or whatever it is?
Oobleck. That's a colloid. You're relating solid to liquid, not liquid to gas.
Okay.
That's the only difference. We'll talk about colloids too. Okay. Here's what's on your page. You see the questions on there? Let's answer these together. Yay, we're doing well. Okay. So yours is a little dark, so please mark the points for me because I'm going to mark them on the other page. So we're looking for what's happening between segment B and C. So segment B to C this is B down here. B is the triple point. C is up here. This is C. So what is happening? What is B to C representing, first of all? What's it between? What's it separating? So it's separating solid and liquid. So every single point on this line is representing what point? Or what phase transition? Melting, freezing, right? Because if I go from solid to liquid, it's melting. From liquid to solid, it's freezing. Every single point there is representing melting point and freezing point. But there's another way to explain this, and this is what you're writing for me. It is the physical equilibrium between solid and liquid. And then I'm also going to say that it's every melting point, freezing point of the substance. Just kind of abbreviated that there. So physical equilibrium, what that's saying is at that point there's both solid and liquid present. But for every solid that changes to liquid, there's a liquid that changes back to solid. So it's in equilibrium. They're both equally going back and forth, back and forth, back and forth. That's what I mean by physical equilibrium. And the reason I say physical is because these are physical states of matter. All right, so the rest of these will be easy because we know how to answer based on the first one. So A to B now. A to B. B is still the triple point. A is over here at the lower left corner. So what is this area representing? Solid to gas. So it's the physical equilibrium between solid and gas, and every what? Sublimation deposition point. Good. You guys are getting my abbreviations, right? Make sure. Okay. And so what's the equilibrium there? Every solid molecule that goes to gas, there's one gas that goes back to solid. And so B to D. B to D. Yeah, B and D is up here. Good. So this is physical equilibrium between liquid and gas. Every what? Boiling point and condensation point. Good. And so there's a liquid that goes to gas, and every gas, and there's one gas that goes back to liquid. That's equilibrium here with the two-headed arrows. Okay, so tell me your observation. You guys have the paper, the graph in front of you. What's happening to, I'm skipping 4 because we just went through what normal was. What happens to the melting point of the substance as the pressure increases? Look at your graph. What's happening to the temperature of the melting point? It what? Decreases or increases? Look at your substance. It actually is, the point of it is decreasing. So here's the melting point here. As you increase the pressure, you're going from, just drop it there, thanks girl. As you increase the pressure, you're saying, let's say 1 atmosphere pressure here, it's melting point is that guy. But as you go over here, the melting point is lower. So the melting point is decreasing. So the way you can know that without even really looking at the data is that, what's the slope of this line? Negative or positive? Negative slope. So the negative slope represents that as you increase pressure, the temperature is going to be decreasing. Yeah.
But the top of the graph, you can stare at it correctly.
No, because that's going to say only solid at the bottom left. Usually, except for that little bit that's gas, but only solid. That would be the critical point up there. Okay. So regardless, if it's a negative slope, you'd say that the melting point temperature decreases due to the slope. Now, this is water that we were talking about on this graph. Water is like one of two substances that have a negative slope. Most graphs look like this. So a positive slope between the solid and liquid form. So most substances, when you increase their pressure, you're really going to have to crank up the temperature, because what's happened is the increased pressure pushes the molecules even closer together, so you're going to have to heat them up more to make them kind of eventually come apart. Water forms you guys know what water looks like in ice phase? It's like a hexagon. Water looks like, so there's like a water molecule here, 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 and here. So there's like nothing in the middle. It's not air, it's literally nothing. So that's why ice floats, because it's got emptiness in it, which makes it less dense in its liquid phase. Most things are more dense in their solid in their solid phase. Okay, so then looking at number 6, definitely positive slope between the liquid and gas phase. So what's happening to the boiling point as you increase pressure? They what? It raises, right? You're increasing the temperature at which it boils. Because the more pressure pushing down on top of a liquid means you have to heat it up even more to escape that atmospheric pressure, which was what caused this. Yeah.
That's why, like, in a vacuum, water will boil even though it doesn't heat.
I can make water boil below 100. I'll do that tomorrow for you. Yeah.
Is the space between the water molecules a vacuum, basically, because there's nothing in there?
I've never heard of it that way. But probably so. Interesting. Yeah. Okay. And I have one more for you. Can I have 5 more minutes? Are you okay for 5 more minutes? Okay. So, what was the name of the graph I just showed you? Phase diagram. This one is called, ready, it's called a heat curve. Is it curvy? No, sure not. Don't know why, but we call it a heat curve. It's not, has no curves on it, period. But you need to know that this is also a way to represent phase changes. So heat curve is the name of this guy, and it has important information on it as well. This is on your chart, on your notes, right? So make sure you know temperature is on the y-axis on this one. What was on the y-axis of the other? Pressure. This one has a couple of different x-axes, okay? It can either be time, it can be heat added, or it can be kinetic energy added. There's like 3 different things that you can put on the x-axis here. So you can see that this phase is on the slants. The slants are where the new phases occur. So there's a solid phase on the first slant, a liquid phase on the second slant, and a vapor or gas phase on the last slant. So what is happening on these plateaus here? Phase change. So what's the first phase change? Melting here, and vaporization, evaporation, or boiling. Good. Okay, so answer the question for me. This question here, what on the graph represents phase changes?
The dashy line.
Not the dashy line. The flat line, right? The flat line or plateaus. I'm not putting plateaus. I'm pretty sure I can't spell plateaus. Okay, so that's where the phase changes occur. And then what do you notice is not happening at during a phase change? What is not changing? Right, temperature. So if I say something melts, you know that the energy within the substance is increasing, but the energy is not influencing the temperature. It's influencing something else. So here's what I want you to write for this part, because this is like the most explanation-based question ever. You have to say, the temperature isn't changing. I'm just going to write it over here now. The temperature isn't changing during phase change due to the energy being being used to overcome the IMFs of the substance. After you write that, tell me what IMFs mean. Intermolecular forces, thank you. So solids are really close together. So as they start to melt, they're increasing in temperature right here as it increases. So as the solid increases in temperature, they're getting more kinetic energy, more kinetic energy, more kinetic energy, all the way up to here. As they start to melt right here, the energy is still being added, as noted on the x-axis here, but the energy added is only used to manipulate the molecular arrangement. It's not used to heat it up, it's used to rearrange the atoms, or space them apart more, and that happens again and again and again throughout phase change. Whew! Chapter 13 done, people. Okay, that's it for chapter 13. So I'm going to let you guys practice in partners on, you can see, phase diagrams and heat curves. Phase diagrams and heat curves. This will take you 20 minutes. After that, we'll do our activity. Okay, you still have 45 minutes left in class. Awesome. You guys are the best group. I did much better. I did much better. My first grade. I'm apparently extremely slow in first grade. Okay, so work with up ready. Stay on task. You will have to draw some stuff on section 1. I probably didn't have that. You will have to draw something on section 1, so you might want a separate sheet of paper for this. If you want to move to relaxation, it's fine. Get her done. Extra? I was too. Man, we're doing a fun lab that day. Maybe I can switch it. I'll do a web quest that day, and you guys can make up a web quest versus a lab. Oh, what would you rather make up? Web quest than a lab. The web quest is easy. Okay, you guys can make a decision. Tell me if I'm switching my 14th and 15th grade or not. It's on that suggestion. Maybe you're not really.
I'd rather do it.
Is the web going to like
And then after that, you'll send the work. So just something that I'll be like it's practice.
Question about the allowers.
Okay.
What would be like the opposite
Yeah, so it's more of a physical process, but you guys were comparing physical to chemical, weren't you? In your research paper?
Oh, I guess
You were, and so is Alka-Seltzer and water. You can do vinegar and baking soda if you want to do it. And then, let me see what I can think of that would be more moles of gas, because that's what oh, and I found this. This, I was looking through some of my AP stuff, and this was like randomly in here. This is what we tried last year. This is not extremely technical, but this is, well, like it's showing me how to like put
Maybe
together
we
the
can use the
card.
bottle.
Yeah. There's a balloon there. So, I mean, that was for balloon material. But I don't think I was going to throw it away, but I can't do it in case
What if we
you
did that thing where it's like, where you put the like the chemicals in the bottom, chemicals in the balloon, and then you put the balloon in.
But then you have to have a mechanism that where the air can escape, because the air escaping, that's pushing in opposite directions, like when you start choking out.
So,
So you have to find a way to get the air to escape, maybe a pinhole or a
Just fill up the balloon.
yeah, but if you fill up the balloon, it doesn't escape. There's no cushion.
We could fill the balloon and then release something after it fills up.
Yeah,
And then we can.
or like a piece of tape on the
I'm like,
Put a melting point here.
But then that kind of is a crazy spin off of
It's
the.
not just.
It's not a direct flow of air. So that's why that one's has a straw, but that was a little part. That's just like, pre
it's a double. Just put all the
contents.
and then just close it, and then watch it expand, and then it's already connected to the car. And so then, once it,
Really suited hand.
yeah, it's,
See how it works. You're
Or-
probably gonna have some problem here.
So like, yeah, there would be a lot of things to be talking about.
it's a big,
Are we like strapping the wheels to a bottle?
I've seen another one like the seed disc has the wheels because they're really thin, so there's no friction.
you get like a really big clip, like one of those, one of those where you push it down, it just clamps. Like a long clamp that can hold maybe 3 cars at the same time, and then we don't really know.
Oh, yeah, I see the call control. I like that too. Or these little things.
Like a whole like
Um,
a big whole bunch of stuff like that.
Yeah, but I was gonna say we could like
That's like a long version of that. I'm not sure how to
get like a ruler and clamp them all, like the balloons down and
and
open
then
it
get
up.
some else on to push all 3 down.
We'll figure it out. Start on what you can on that, and I will help you as I revise it. Because it's one of those things that off the top of my head I always keep thinking, but when I'm reading it, I'm like, oh, I have this, have this, have this. So I'll think of some more information. So you just add that to your computer. Finish this worksheet. Here's what it looks like. So your question's pretty much established. Our hypothesis is established, but it's just I need you to write it in a more testable manner. Your experimental variables. So you guys are doing fruit batteries, right? Okay, so you're probably gonna say we'll test fruit 1, fruit 2, fruit 3 with you're getting charged with a knife or something like that, right? Okay. I guess you would just test different fruits. I don't know if you're gonna test the different fruits at different temperatures or something like that, like a hot fruit, a cold fruit. That might make a difference, or old fruit versus a really ripe one. I mean, a new versus a ripe one. So you could add a little bit to it, but basically that's what levels and trials mean. But your variables will be like, what are you changing in the experiment? And then what are you testing in the experiment? Your constants would be like, same size fruit, tested for the same length of time, same brand of fruit, like those little things that are just the same across the board. And then down here is basically tell me what he's going to provide, Lou's going to provide, what I'll help provide because I can help with something. And that gives me information about what I need to get, if I need to get anything. And then this is like the procedure. And then safety.
Okay.
The last thing is data. Basically, as you write your procedure, you'll say collect data, collect the voltage here, mass it here, and you'll make a data table as you write your procedure.
Okay.
Does that make sense?
Yeah.
Okay. There's a rubric on the bottom too.
Okay.
did you see the?
I started look last night and I finished grading a bunch of stuff and I haven't finished making comments on yours. Okay, but I can revise that as I go. That's not due yet.
I was waiting on that.
You're not coming?
We'd like to make up a $1.
Okay. I'll switch.
Yeah, that's what we said.
No, he's not.
No, he's taking his test. Yeah. Because he's in the background taking his tests. Because he went to it. Yeah, come today and I'll help you guys get some steps.
I don't know if it's like, I can't come after school because I'm working.
Work in the week? This isn't happening.
It's happening. I took off Saturday to find grandma died. She just
So you just had to make it work for you.
I was just gonna drop all of them.
What are you doing, Jack?
I lost my leg.
Get your life together. Okay, I'll switch dates for you. Yes, you guys can make up the left.
This one, I said it could be time or kinetic energy. You don't have to really just because that there, it's a bit. I'm still thinking, hold on, I gotta show this video. She doesn't know. See? Oh, it's not, I hate when you're